Chapter 4 covers the concept of polynomials. Now, polynomials are something that you've come across before, probably just not referring to them as polynomials. In this chapter, we're going to revisit things like factorising, zeros, graphing, but probably in a bit more of a formal way. This very first exercise looks at defining terms. We won't get too bogged down in that. It's only that you won't certainly be asked for the definition of a term. But if you came across a particular word in a question, well, you'd need to understand what the term was referring to. So that's what we'll cover in exercises 4A and B. For C, D and E, look at working with polynomials. Now, we'll be dividing them. We'll look at this thing called the remainder theorem and the factor theorem. I think the reassuring feature of this whole chapter is that once it was offered as an option at the end of Year 10. So keep that in mind. There's nothing really difficult about the concepts. It's just broadening your, vocabulary, and looking more widely at how to work with expressions that you probably haven't done previously. There's always more maths, just be reassured that you don't have to always go to harder maths, but you can just go to different maths. And I would say that that's what's happening here in this chapter. Okay, let's move on. So a polynomial function and a function, we have an understanding of the word function. We can graph functions. We usually graph them on an XY number plane. And it can be written in as a sum of terms. Now, you'll see in a moment, n can be anything from 0 through to, anything as big as you like. So our first term, and we arrange it always, our polynomials in this order, where our x term with the highest power appears first. This an is just the coefficient. And then we've got, so if we've got, say, a cubic, so we've got our coefficient of our x cubed. We've got our second coefficient, and it's of our x squared term. We've got our coefficient of our x term, and then we'd jump straight to here. We've got just a constant. N, then, it represents the degree. So it's important to know that. So if the degree is, if n is 1, we would say it's a linear function. X to the power 1 is linear. X to the power 2 is a quadratic. So these are things, like I've been saying, that you've come across before. If n is 0, x to the 0 is a 1, and we would just have a constant polynomial. You've actually seen those. For example, y equals 2 is the horizontal line through y is 2. If a to the n is 1, so the number here at the front of your highest power is a 1, I think you've come across this before. It's referred to as monic. So it's really reinforcing some of the terms you've come across before as well. A 0, the number on the end with no x attached to it, is called the constant term. It represents where the graph cuts the y-axis. A n x to the n is called the leading term, and that's why it's important that we get it in order from x with the highest power coming down until at the end we have x to the 0, which doesn't appear because it's 1, so it's just the constant term. No, the word leading term. The opposite polynomial is just minus all of the polynomial p of x. So it's just like putting a minus and a bracket out the front, and you could produce the opposite polynomial. And the zero polynomial is when all your coefficients are zero. And that's fairly special, so it's actually just zero as opposed to a constant. That's the zero polynomial. We could have a polynomial expression, and we can have a polynomial equation. Most of them in this format would just be the polynomial expression. It's a string of x terms being added. The role of the p of x is just to name it. This just names it. When I take that out and I put my expression equal to 0, then I have an equation. So 3x to the fourth plus x squared minus x is an expression. This 3x to the fourth plus x squared minus x is equal to 0 is an equation. So, yeah, we're really paying attention to the detail of the words. Because a polynomial is a sum, it can be represented using this sigma notation. And I think we've dealt with that before. So k could be 0. Now, if k is 0, then we would start with our constant term, wouldn't we? Then we'd have our x term when k is 1, and then we go k is 2 and k is 3. So it's actually the reverse of how you commonly see the polynomial written. So we commonly see our polynomial written with the highest power of the x first, whereas here, when we start to apply this, we're applying our k is 0, so we have x to the 0, which is 1, which the x actually disappears, and then we do k is 1. So we've got our x term, then our x squared term, and so on. It's just the reverse of the above expression. Zeros or roots, there's just a minor difference. The term root is used when we refer to the graphical representation, so where it cuts the x-axis, whereas zeros is what we get when we solve the equation equal to 0. So it's more the algebraic answer to the polynomial equal to 0. They should be both the same answers. Roots and zeros will be the same number. It's just roots is referring to the place on a graph, and zeros is referring to a number to put into an equation to make it true. We've talked about the zero polynomial. The constant polynomial is when there are no x terms. We talked about that. A linear polynomial, you're very well aware of. Quadratic, you are also. Then we have polynomials of higher degrees, because once we start to increase the power up to a 3 or a 4 or a 5, so on, we just say they're higher degrees. And if our polynomials are identical, which we've seen before, and we actually worked with this, we know that if the statement is that two polynomials are identical, we know the coefficients of the like x terms must also be identical. And we actually used that, I think, way back at the beginning of the Year 11 course to work out some coefficients or some unknowns. Operations with polynomials, we can add and subtract them. You've done that before. And you know that you have to have like terms, and we simply group together our like terms and add and subtract the coefficients. We multiply polynomials, so x plus 3 is a polynomial, x squared minus 2 is a polynomial. We multiplying these two polynomials, and you've previously seen that as an instruction to expand that, but it really in essence is just multiplying polynomials. You've factorised polynomials, and we looked at factorising and all the different methods of factorising and the advantage of factorising. Division. We probably haven't done much on division, and that's where it's going to be quite an emphasis on division. So if I take a polynomial and I've got a divisor, what's left is the quotient and the remainder. And there's not always a remainder. And we're going to actually revise some long division, but we'll go through that. Don't panic, we'll go through that. If the remainder is 0, then that's a factor and that's a factor. They're factors when the remainder is 0. But we know that. If I put 3 into 12, I get 4 with no remainder. We know that both 3 and 4 are factors of 12. If I put 5 into 12, 5, what do I get? 2 and 2/5. I've got a remainder. 5 is not a factor of 12. 2 is not a factor. 2 and 2/5 is not a factor of 12. So it's just really based on that concept. Okay, now, which of these are polynomials? Well, yes, it's really all about the powers. So can we have an x squared? Can we have an x? Yes. Can we have, well, that would equate to x to the minus 2, and the answer is no. The power cannot be a negative, and the power cannot be a fraction. And x cannot be in the power. And again, we'd have a negative x here, so it's a no. An x cubed is fine, an x to the 1 is fine. An x with a fraction index is a no. So there. Just reinforcing that the indices on the x has to have, well, can't be a negative or a fraction. I think that's the easiest way to remember them. This next 3 examples is just reinforcing the understanding of these terms: degree, leading term, leading coefficient, constant term, and whether it's monic. Now, most of that you've probably come across before, so I'll leave that for you to maybe pause the video and have a look at those answers to those. Find all the zeros. We would know that we would put our polynomial equal to 0 and factorise, etc. So you can see that I've done that there, factorised. This is all really just revision, it's nothing new. The polynomials p of x and q of x have degree p, so the highest power of p of x is a p, and this is q of x has highest power of x is a q, and p is bigger than q. What is the degree of when we multiply them? Well, think about what you do to your indices when you multiply your x terms. You add them. And what do we do when we add the polynomials? Well, the highest degree doesn't change. What difference would it make to the product and the sum if they had the same degree? Well, still the same. We add p and p, so it becomes 2p, which is bigger than p plus q, if p was greater than q. But the sum still has degree p. An example of 2 polynomials, degree 2, so highest power is 2, and the sum of the degree is 0. So which have a sum. So we sum those two, the x squared terms eliminate, the x terms eliminate, and we just have a constant, which is degree 0. A monic polynomial whose degree, so it's monic. What does that tell you? It tells you the coefficient has to of the leading term has to be 1. So we've already set the coefficient, which is this, the leading coefficient has to be 1. So then the constant term has to be 1, and the degree has to be 1. So it's just x plus 1. You've done questions like this before in the Year 11 course, and the video is about to run out, so I'll leave you to pause that and go through that as you need to, and then get started with exercise 4A.